Hello, and welcome to February's webinar from Erlang Solutions. We're with Fred Hebert, and he's the author of Learn You Some Erlang, Erlang in Anger, and his latest book, which is Testing Erlang and Elixir through PropEr modeling, which is what we'll be discussing today. So Fred will be talking about one of the most powerful techniques when it comes to property-based testing, which is modeling, and we'll be looking at stateless and stateful properties from that. So before I hand over from Fred, if you have any questions for the end, we'll be doing our usual Q&A, so you can tweet us. Our handle is @ErlangSolutions, or you can submit a question in the question box on this GoToWebinar platform. We'll be having our Q&A session at the end, so knock any questions in there and we'll get through them all. So without further ado, I'm going to hand you over to Fred. So take it away, Fred.
All right. So as mentioned, I'm Fred Hebert. You might also know me, if it's not through the book, as being a Rebar 3 maintainer and having opinions on my blog with the link right there. As mentioned in the introduction, this is about property-based testing with PropEr, Erlang, and Elixir, specifically about modeling as an approach to property-based testing. And I want to give a little additional warning since we only have 1 hour for this. You will probably not be able to go back into your projects and apply all of that stuff if you've never done property-based testing before. So if you're entirely new to the topic, you should consider this presentation as a kind of a quick tour of the possible approaches that you have and what kind of stuff you can do when you approach property-based testing, because you will get far more details in the book itself, unsurprisingly so. If you do know property-based testing, though, and you've been through the content, it might be a helpful presentation in showing a bit how I approach personally building models and the kind of structure I put in there. But since we might have people who have never done property-based testing at first, I'm going to start with the basics and do a really quick tour about how it works, what is property-based testing, and that kind of stuff. So the best way to compare property-based testing in general is to compare it with usual traditional example-based testing. And so here I have a merge function, right? And as a developer, the merge function is kind of simple-ish to test. We have a general idea that, for example, we might have a bunch of, it's a list of lists. Each of the lists should be sorted in order, and I know that because I looked at the documentation. And the result I should have is all the elements of all the pre-sorted lists are merged into a single list. When I try to come up with examples of that, I have to kind of anticipate the regular use cases, pick a bunch of examples that demonstrate what I want the function to do in the usual case. And then I also have to come up with all the kinds of edge cases that might exist. So you can see the first 4 cases. I might decide that an empty list is an edge case. A list with a single empty list is an edge case, with 2 of them, with 3 of them. And then as a reader of the test, you have to wonder if the 3 empty lists is a special edge case, because, for example, we might be using a 2-way or a 3-way merge in the implementation. Or if there is no further edge cases in 3 lists than you would have in 4, and then the person writing the tests just got tired of that, right? So the kind of risk that we have with example-based tests is that it is limited by our experience and imagination in coming up with kind of edge cases and surprising conditions. And as a reader, it's not necessarily obvious what are all the rules that are required to implement to do right. Right, so we can assume, for example, from the last example at the bottom, that it supports an infinite number of internal lists, but it might very well also only support 9 lists and none more than that. We don't necessarily know. We kind of assume that if it only supported 9 lists, it would have used 9 arguments in the function, and that's about it. When we work in properties, we can change things in the approach to be a bit more general there. And this is a property in Erlang. This is a similar one in Elixir. I have the snippets in both languages, and I'm going to jump between them. What this one tells me, without knowing the syntax already, is essentially that if I get a list of sorted lists of integers, then my merge function should be equivalent to appending all these lists together and sorting them. And so what is interesting with this property, even if you don't necessarily understand the syntax right now, is this kind of idea that I'm stating that the premise of my test is that you have a list of sorted lists, right? The list of sorted lists is kind of put explicitly in there, but was extremely implicit and inlined in this example. The other thing that it tells me is it compares the implementation I have. The function that merges my list of lists is equivalent to another function in there. And what this is telling me is that there is a general behavior. No matter what example you come up with, no matter what edge cases you have, those two implementations should always behave the same. And this is the core principle behind modeling. So I'm going to come back to that, but the idea of a property is that you write a kind of condition that is always true, and then it is the responsibility of the framework to come up with a bunch of examples according to your specification to make sure that it is the case. And so this property and this property is about 3 or 4 lines of code, but when you do that, you can generate 1 million tests out of it, which is pretty sweet as a deal. The basic syntax that we're going to use for properties in both Erlang and Elixir looks like this. We have in Erlang a header file from PropEr to include. I assume that it's all put in your deps, and you know how to do that already for the sake of the presentation and going a bit faster. In Elixir, you go into your test module and you use the prop check module that will import all the macros that you need. And properties have 3 basic ingredients. You've got the top property function with the for all macro. And the for all macro requires the 2 other ingredients. The type generator, which is a specification of how the PropEr framework should be generating you the types of data. Here, the type generator is defined as a list of integers. And so it does not tell us what integers are in there, if they should be sorted or not, or all that kind of information. It's just any list of integers will be used as a generator. This generator gets called for every instance of a test. You can have only 1 test, you can have 100 of them, you can have 1,000 of them. Each of the instances, in turn, will be bound to the instance of type variable. And so when that list gets into instance of type variable, you are able to call it into the property expression. The property expression is the actual test. The thing that you check is always true, right? So the merge function of sorted list should always have the values all in order. That could be a property. The property expression has to return true or false. And that's about it. Those are the 3 recipes. But to think in terms of property, I will use the kind of idea of the flat earth theory. And the flat earth theory is a very good theory if you can only do local observations a few centuries ago. And the flat earth theory is easy to prove or to demonstrate if you're using example-based tests, because you can go into a flat area in the land and see, like, no matter where I stand in Death Valley in the US, for example, which is a very flat place, the earth looks flat. The only reason I cannot see the edge of the world is because there are mountains, and then at some point I can just not see far enough. And so if I wanted to write unit tests for a flat earth theory, I would probably pick something like, I don't know, 5 to 50 different points and say, like, any of these points I can see myself at the other end, and so therefore the earth is flat. Or at least for all intents and purposes. For my program right now, the earth being flat is sufficient for me to do things right. But it is not necessarily true. But if I have no idea that the earth is not actually flat, my testing approach will not tell me about it, right? Example-based tests only let us prevent the bugs we know might be there. Property-based testing is a bit more interesting from that point of view, because since we have to come up with a rule and the framework comes up with the examples, there is a far higher chance that the framework is able to give us tricky inputs that break the rules and let us figure out that we were wrong about what the rule is. And so if I wanted to test that the earth is flat for any pair of coordinates on the earth, I might come up with a procedure such as if you go straight up, right, for I don't know, 50 or 100 meters, then you should clear most obstacles. And then I should be able to point a laser pointer between these 2 areas at 90 degrees, and then they should be able to see each other. And if they can't, well, there's some weird angle going on, and so the earth might not actually be flat. And so if I wanted to test that as a property, I could create a property for the earth is flat. And I would have a generator that gives me just 2 random coordinates in the earth and goes about it. And then my property check or my little test would be, can my 2 points at higher altitudes target each other at 90 degrees and then perceive the laser or something like that? And so this would be true for all the examples where the coordinates are taken in a very flat plane or in Death Valley or something like that. But if the 2 points are very far apart over the ocean, then all of a sudden the property fails. And so I have to figure out whether my implementation of the test is not right, or maybe actually the Earth is not flat. And I can do that because the way that data is generated can exercise things in a pattern that I, as a test and implementation writer, didn't see coming. So to get back with something a bit actual, we're going to make use of a few default generators in here. The PropEr framework comes with dozens and dozens of generators. This is a few of them. Any generates any generatable Erlang terms. You can have atoms, binaries, Boolean values, integers in a range, floating point numbers, integers individually. You can see that generators can be composable. So you can have a list of another generator. The little sample that we have here is a list of Boolean terms that returns true, true, false. You call it again, it might be false, true, false, or something like that. It's a bit random. You can have constraints like non-empty is applicable to either a list or a binary. And what it does is make sure that you never get an empty list with nothing in there. There's always a value in that one. A number is either a float or an integer. There's a string type that is used almost exclusively in Erlang. I think the prop check variant or wrapper in Elixir does not expose string. Instead, you actually use UTF-8, which returns a binary with UTF-8 content. And that generator is also available in Erlang, and then you have tuples. So there's a lot more generators available, but this subset is going to be more than sufficient for this presentation. However, a generator is not just a little function that returns a random value. A generator returns you a kind of big-ass abstract data type like this that contains more or less a description of the content it has. And so there's the proper colon integer type. And if you call it, it just gives you that kind of environment generator, instance shrinkers, and basics. If you put that generator into the list generator, you can see that the integer is within the internal type tuple. And then it's that way, and it all composes. And so if I want to play with the values that come out of that, I have to do it within the context of a proper property. So when I use the for all macro and I bind the little value that I have into the instance of type, PropEr takes that huge tuple, extracts one value or one example value, puts it in there, and calls my property. So if I want to make something special with these generators, like customize them, I also need my own macros. And so we're going to make use of a few of them. The first one is the let macro. And the let macro takes a generator, gives you the example as a variable, and then in the expression, you can modify it. You can see it in the queue function as an example, right? I want a list of tuples. Take that value, put it in the list variable, and that list variable, take it and put it in queue from list. The call to queue from list there is executed within that structure. All that the let macro does is take that little body of a function and put it into that abstract data structure. And so with this, we are able to say this is not only a proper generator, this is a proper generator where you apply custom transformations. So instead of just running a list of tuples, now my generator is actually going to return queues every time. The other macro is such that. Such that as a macro is similar to the let macro, but instead of applying a transformation, it lets us put a constraint in place. So the precondition that you have here, it's the remainder of a division by 2 is equal to 0. Lets me know that the only values you can let out of the generator are going to be even numbers. And if a number fails to be even, PropEr will know to retry the generator over and over and over again. Also, a quick thing that's a bit off topic. You will notice that I'm using a programming font with ligatures in there. So don't be surprised if you don't have these exact operators. This is just fancy looking stuff. For this presentation, we're going to use a tree as a case study. A tree is essentially a key value data structure. You don't have to care about the implementation. This slide is just because I needed to put something in there. We could use anything else than a tree for this presentation. We could be using a map. We could be using an AVL tree, a red-black tree, a web service that lets you store keys and values. We could do it over Amazon S3, where the keys are paths and the values are binary blobs or something like that. Since we're using modeling and whatnot, really what we are concerned about is the key value approach. But I had code for a tree laying around, and so I picked a tree as an implementation to play with. And the interesting aspect of a tree is that instead of having complex rules for rebalancing the way an AVL or red-black tree would, where there's something like 4 or 6 different types of rotations, a tree is probabilistic and only has 2 rotations, so the implementation is kind of straightforward. So the question is, how would we test with properties a tree like that instead of just inserting and removing the keys? And an easy way or a common way that you might see, actually it's not easy, it's really hard, but it's shown as easy if you're coming to property-based testing from, let's say, Haskell or another place where they do a lot of type-based property-based testing. And what they come up with are complex invariants like that. I don't expect you to read them and understand what they are. Invariants are super neat when you can have them. They're just a basic set of rules and simple checks, and you say that if all of them are right all the time, then you know that the data structure has the right format. And so I could have an invariant for a sorted list that would be each element in the list is larger or equal to the one that precedes it. That is a simple invariant that when you apply it to every element, you know that the list is actually ordered. The problem with an invariant is that to know that you have all the invariants that you need, that all the invariants that you've chosen are sufficient to demonstrate that your program is correct, is essentially equivalent to developing a mathematical proof. And so it's really, really hard. For a tree, it's super easy because you just pick up the paper that you have or the Wikipedia article that will list out all the invariants. You put that in the test, and so you can go ahead and whatnot. But that's an extremely limited set of circumstances where you can do that. And so instead, what we're going to do is use modeling. And modeling is really, really fantastic from that point of view because modeling is easy. It's easy to get going with. It might be a bit tricky to get right, but essentially modeling requires you to have an implementation that can usually be complex. You try to be effective and efficient and fast in your implementations. And so you take all kinds of little extra measures that add complexity to the system. And so I could take this example here. I have a washing machine. And the true washing machine has a lot of complex machinery in there. And the whole objective is that it's faster to wash clothes than doing it by hand. So usually I have a simple behavior as a user, but the implementation is complex in order to have all kinds of characteristics that I find desirable in a system or in a module or in an implementation of something. The model by comparison is super fun because a model has to be simple, so simple and straightforward that it is hard to think it is incorrect. It doesn't have to be fast. It doesn't have to be effective. It doesn't have to be memory efficient. It doesn't even have to satisfy all the requirements that you have. It just has to be simple enough that you can compare the implementation to it. And so here I took a very simple manual washing machine. And so if I wanted to test a washing machine, I could make a model that would be any piece of clothing that I put dirty in a washing machine comes out clean, should be coming in as clean or cleaner than a manual washer. And that could be a property. And I could just come up with a different property that has nothing to do with it. That would be whenever I put the clothes in the washing machine and I take them out, they have not been damaged more than if I just dunk them in the bathtub, for example. And so I would have a model for cleanliness, which is a manual washing machine, and I would have a model for the quality or wear or tear that I put into my clothes that would be dunking them in a bathtub. And when I have 2 or 3 of these models, I have a bunch of very, very simple criteria and comparative tests that I run against my actual system that is complex here. It's 6 washing machines with timers, with payment mechanisms and all that kind of stuff but I can demonstrate that they work as well or better than my model, and they're usually faster. And so the model is really, really fun from that point of view, because you just have to make something so simple you cannot be wrong with it that demonstrates the point of view you want to have. And that's it. You just compare your actual system to the model. And so here I could be modeling a tree or any key value structure. As I said, it could be a database that uses 15 nodes in the background. It doesn't matter. I'm just going to use a list of keys and values. And you will see here that I gave myself a little from list function, a lookup function, a smallest, largest insertion function that just uses list module operations. In Elixir, the model is roughly the same thing. I use enum, min, and max for smallest and largest, but all the other operations use just list key operations, and that's about it. If I compare this to, say, the implementation in the tree, and let me grab the implementation of the tree. Yeah, I'm going to do it in Erlang. I only have one implementation. It's the same language in all cases. If I go for a tree, a lookup from list operation, smallest and largest, has recursion. It's a bit more complex. Insertion can call to rebalancing. And so the machinery of the actual tree implementation, which you don't have to care about, just turns out to be a lot more complex than what I have in the model. That's the important part. So when I write a property, both in Erlang and Elixir, the thing I want to do is use the for macro. And I'm going to generate a list of keys and values. Here in Erlang, it's not empty list of a tuple of numbers. If I look at the Elixir implementation, still on the second line, it's a non-empty list of numbers that I bind to the list variable. And what I do with my model is that I'm going to call my models from list implementation. And then I'm going to call my trees from list implementation. And then I'm going to test the smallest function. So the smallest value of the model should be equal to the smallest value of the tree. And the largest value of the model should be equal to the largest value of the tree. Whatever the actual system does, I make it happen in the model, and that's it. If they both agree, and my model is so stupidly simple that it should be correct, then I can infer that the tree, which is far more complex, or the database with 15 servers, which is far more complex, is also behaving correctly, because it agrees with the so simple, it has to be right implementation. And so the Erlang implementation is exactly the same. From list in the model, from list in the tree, small list in the model is the same as small list in the tree, and so on. The second property I have here is for lookups. And so in that case, you will see that the list I generate can be empty. It could not be empty with the smallest or largest implementation. Both of them had the little non-empty composition thing. Because there is no valid value for which an empty tree could return a largest or smallest value. So what I do for that one, I still convert the model in the tree from a list. And what I do for that one, if you're not familiar with the Erlang syntax, wait for the Elixir slide, is really I'm extracting all the keys in my original list. And for all the keys, I'm going to look them up in both the model and the tree. So I make sure that all the keys I had in the original list also end up in the other thing, and I get the same result for both implementation. I also add a test on the last line there, which is using the makeref call, which is a unique value. That one is just a test to make sure that when I read a value that is not in the tree, both implementation agrees. And so in Elixir, it's kind of the same approach. I extract all the keys within them all and do the lookup in both implementations. And so this should work pretty well, right? As long as my model and my actual system agree on what should be returned for all kinds of little cases, I will get the same result. When I run them, though, I find bugs. And so this is how I run only this module in Erlang. You can see that the first property with model sizes failed. It had initially a list with 3 keys and values that were distinct. And then PropEr did something called shrinking. And shrinking is the action of taking that test that failed and trying to simplify the values that it has. It tries to shorten the list. It tries to reduce the size of the integers and all of that kind of stuff. And then it gives you a smaller counterexample there with 2 keys set to 3 and 2 distinct values. The second test fails kind of the same way. You have instead 8 or 9 values. It shrinks them to a smaller thing, and then it tells me that the property failed. If I want to run it, in Elixir, because we're doing this multi-language, I'm going to run the same test there. Elixir asks us to remove this kind of little project context thingy to give you different results every time something fails. And you can see that I'm getting failures. The output for Elixir is a bit different. By default, it doesn't show you everything, but it only shows you the minimal counterexample. And you can see that every time I run it, I can get different examples. It is probabilistic. There is no guarantee that all the bugs will be found every time, such as this time, where it only found one counterexample to one of the properties, which was the lookup, but the smallest value succeeded. If you run them enough time, you're guaranteed to find all kinds of bugs. Well, not guaranteed, but the chances are very high. And so I could run it 1,000 times here, and much before that, it will find my issues that I had here. So if I wanted to figure out what the problem is, I can look into all the little outputs that I have, and it seems that the problem is really related to duplicate keys and values. And the bug that we have in the tree is that if you look at how the function to insert values is implemented in the tree, what it does is inserts the value one after the other in the list. And so if there is a duplicate value, the latest duplicate value seen is the one that wins. When we go back to our tree model, which was here, you can see that the from list implementation is just returning the list itself. And so all the duplicate values are left as is. So what we found is that there is a disagreement between our model and our property and our actual system. So what we have to do, well, what we just did essentially is we found a new requirement in the system. It was not obvious, and there's a crap load of code out there in the wild that does exactly the same thing. The little utility function from list or from enum or from whatever has made an implicit decision of how it is going to handle duplicate values. It is not documented. It is not even a conscious decision, but it exists as an implementation detail. And so we have to make a decision of how we're going to handle this. We can handle it by erroring out if the original list has duplicate keys. We can handle it by keeping the earliest value seen, or we can handle it by keeping the latest value seen. And so what we can do at that point would be to change either the model or the implementation or both to agree on a new decision. To make things a bit simple, here I'm going to with an implementation where what I'm doing is taking the list and aligning the model with the implementation. And so what I'm going to do is reversing the list I pass in and then just checking for every insertion that it is different than one that already exists, otherwise it is ignored. And so that fix to the model essentially tells me the model will also keep the first value, the last value it has encountered as the one that wins. I'm aligning the model with the actual system. And now, if I do run the properties with this, let me get this going, we will see that we have much nicer values or much nicer results. And so the value is fixed, all the properties pass. I have the invariance properties, which is why it shows 4 tests instead of just 2. And so it worked. And I can generate as many properties as I want. I have 3 examples. And so basically with the few lines of code I have there with the model, I just ran at least 20,000 instances of my modeling checks. And all of them are passing. And so I can be pretty sure I'm getting decent results. It's pretty nice and straightforward as a way to test the operations. One of the problems that I have, though, right now is that I have implemented essentially what is a lookup and the smallest and largest values. But if I want to implement something like checking the deletes, I can generate a tree, generate a list of values to be deleted, and then I'm going to get that. But if I'm working with a more complex backend or storage, I might want to test specific operations like inserting a value, inserting a duplicate value, deleting it, and inserting it again. And so what I'm testing now is no longer just simple operations. It's the interleaving or the result of interleaving multiple operations together over time. And this is really, really hard to do with stateless properties. And so we have to look into stateful properties. And stateful properties is really where property-based testing with at least proper quick check and so on really starts shining. It is super interesting and much more powerful, but it is also a little bit more complex to implement. And so what we are going to generate is, instead of just lists of keys and values and then we run the operations, stateful properties, what they ask us to do is generate sequences of commands and operations. And so rather than saying, here is a tree, run operations on them, I'm going to create operations such as, here's my initial tree, insert a value, insert another value, delete a value, insert a value, look up a value, check what the smallest value is, and then delete a value. And I can do that over and over and over again and get all kinds of sequences of operations. And that's what a stateful property asks us to do. We still work from our very simple model. We're just going to compare our simple model sequences of operations with those of the actual system. And this is a bit complex. Your eyes might glaze over into these sections a little bit. Just know that this is what is required to go through. That's the complexity that often makes people go, well, I'm going only to test the absolute core of my system with property-based testing. This is a bit hard, but the more you practice, the easier it becomes and the more reliable it is. So there are 4 callbacks to generate a sequence of operations. The first one is the initial state. The initial state is just what is your model going to be. And here I'm going to use a map because it's a key value store. It's already implemented, and I trust the virtual machine to have a good implementation. And so my initial state should be returning only an empty map. Command is a generator. Command should return any of the valid or any of the commands that are possible to run on your system. So in this case, it would be insert, lookup, delete, smallest, or largest. Those are the 5 operations I'm testing right now with the tree implementation. Then I'm going to set a precondition. Precondition is a validation that lets you know whether a command is valid or not. So for example, with the smallest or largest function calls, we wanted them to only work, only be called if there is something in the tree, because otherwise we know it's invalid and it's going to error out. We're not interested in testing that it crashes. We're interested in seeing the interleaving of commands that are supposed to go well. And so that will let me so far generate a kind of command that will just let me know that, yes, right now you can actually do a lookup, even if it's an empty tree. And then the next state callback lets me tell PropEr how to increment the sequence of operations. So in practice, those are the callbacks. Initial states returns an empty map. If you look in Elixir, initial state returns an empty map. The commands here are symbolic calls. So it's a tuple that describes a call to a given module. Here it's Shim. I'm going to explain it a bit later. It's not important for the model. This is going for the actual implementation. But I have operations for inserting, looking up smallest and largest and deleting. And these have generated arguments. So this is a command generation. It looks exactly the same in Erlang. The one-off generator that we use in both cases, the little one-off generator just picks one of the 5 entries at random. That's what it does. The precondition implements exactly what I mentioned. The smallest or largest function can only be called when my model state, the map isn't empty. And you can see that it is implemented exactly the same way in Elixir. The last condition tells me all the other comments are always valid. It's not a problem. And then we have the next state. Next state is how do I update my model according to the calls I would make in the actual system. So whenever I want to insert a key and a value in the system, my own state is going to add the key and the value in there. Whenever I delete it, I'm going to remove the key from my state, and in all other cases, it remains the same. And so in Elixir, it's like this. Every time I insert a key and a value, I put them in the map that is my state of the model. Whenever I delete it, I remove it from the state of the model, and next state remains as it is. And so with this, I have created a generator for a sequence of operations. It's a new custom generator in PropEr. And that generator can then be used to run all the commands. The problem is that we are not doing any validation whatsoever of the actual system. We're just described how we can run the model, and the model is a simple in-memory data structure. So stateful properties add a little more complexity with a callback called Postcondition. And the postcondition is going to be kind of injected in the sequence of callbacks that you have to go whenever there was a call made. We're going to give you the state of your model right before that call with the result from the actual system. And what you want to do is, through your model, predict, just guess ahead of time what the actual system should return. The value of a model when doing probability-based testing is directly proportional with your ability to predict what is going to happen, right? Our model of gravity is good because we know that if we drop an item, it's going to fall on the ground. At least that's how it works on Earth. And so the model, the prediction that I have is that if, for example, I call a function to look up a value, and the value is not currently in my model state, well, I should expect in the postcondition that the call to the system returned me that it was not found as an error. And so that's what the postconditions do. I take my model state. I say that when I insert a value, it's always valid. I do no validation and insertion. I just trust that the system will do the right thing. However, when I look up, now I try to predict. If I look up a given key named K, I will look into my state and say, whatever was in my state is what I want the system to return to me in the result. Here it is in Elixir, that's still the third clause. If I look up a key, I fetch it from the map, and whatever is the value is what I want result to be equal to. And the smallest and largest functions are kind of the same. Based on the state I have, the result I expect is to have the validation of whatever I had in there. And when you write stateful properties, there is often a reflex to kind of just look at the output of the result and make sure that it has shaped correctly. But you don't give a crap about the actual system. It is always the model that is in the driver's seat. And what you want to know is that the actual system agrees with the model, not that the actual system, based on its previous result, gives you the right thing. It's based on what the model predicts is the system behaving according to the model. That is the important part. And you will notice that the last clause of the postconditions are set to false. I use that to make sure that if something I didn't see coming is added to the model, it fails and I have to fix it. I don't want my test to pass by accident. So we have all the pieces in place to actually call the system now. And this is where the Shim module comes into play. The Shim module essentially just wraps my tree and puts it into a gen server state so that it looks like it is a mutable store. So you can see that the insert operation just calls into the gen server, which runs the tree operation. The lookup just runs into the gen server, which runs the tree operation. And it's kind of cumbersome to do, but it's essential. It's a bit nicer in Elixir because you can actually use an agent for that. It's the first time I find an agent is like, yes, it is useful to use an agent because you can just wrap the operations directly in there and have them do what you want. And so you can see that the Shim's insert operation, delete operation, lookup operation, smallest and largest are essentially just very, very slim wrappers around the tree to give it this kind of statelessness. And here's what it looks like when we put it into a property. So I'm going to start with, it's prop. Oh, it's in test, sorry. Test prop tree model. The URL. So to run them, I still have a for all macro in which I start the shim. I start the stateful process in the background. The generator I had for the commands with the for callbacks is generated here. Commands called Mojo, which goes called initial state command preconditions and blah, blah, blah. It will run this sequence of commands with the run commands callback in there. And what I'm interested in is the result value here. If all the precondition and postconditions and operations were fine, this is going to result to return me the value okay. If not, it's going to have a bunch of errors in there. And this big bit here is just telling me like, this is how you handle errors. The actual check I want is here. If I run it, if I go look at it in Elixir, it's going to be tree, no, it's model. And the tree model tests, the syntax is roughly the same. I have the commands generator that I put in the for all value. Oh, you'll notice that I put the verbose attribute in here. The verbose attribute makes it so that I will get the same output in Elixir as I do in Erlang by default. So I start the tree shim, I run the commands, I have the result in here. I stop the shim, I check that the value is okay, and if it is not, I do all my kind of error handling. And this calls my precondition, postconditions, everything like that. So if I run this, and here it's going to be trip model test, I'm going to get a bunch of executions and it tells me all operations that ran. So I ran 100 sequence of operations, 25% were delete, 22% were lookups, 21% were inserts, 15% were largest, 40% were smallest. I can run the same one again in Erlang here, which is going to be trip model instead, I think. And so I will get a similar value. The percentages are not exactly the same. I have a few more insertions and deletions in that case, but that's because this is a probabilistic test. It always returns different values. And so they're not exactly the same. But I do have a model now, and I know that the sequence of operations I run are the same in both cases. And the little gotcha that I have is that it's easy to give a lot of trust to that. But knowing that lookups are not always the same, and that deletes are not always the same, and insertions are not always the same, this is a bit opaque. Like, I don't know if most of my lookups are lookups into, if my lookups are lookups into trees that don't even hold the key I'm looking into, or if it's always the same key. I don't know if the deletion is actually removing anything from the tree. Maybe it's always using a new key that doesn't exist. Same with the insertion. Smallest and largest, I can trust to be more or less correct for that. But really the lookup, delete, insertion, I don't have a good idea of how much quality I have in there. And so what we need to do is add more determinism to our model. And here I don't mean determinism as in removing randomness. I mean determinism as in the model is even more predictable. So the thing that happens is that I, as a system designer or as someone who uses it, even know I only have 5 calls, lookup, insert, delete, smallest, and largest, that based on the context, those calls don't always behave the same. Lookup does not behave the same when there is a value in the tree and when it is not there. Delete does not behave the same when there is a value in the tree and where it is not there. And insert also does not behave the same in both cases. Smallest and largest remain the same. And this is where the Shim module becomes really interesting. And this is why I always use a Shim module when I'm doing stateful property testing. The Shim module lets us enrich the model's predictions without changing how we call the system underneath. And so here's my new Shim module. I have divided insert, lookup, and delete into 2 operations each. One when the value exists and one when it is not known. And so you can see that insert new and insert existing both call the same insert function in the actual system. Lookup unknown and lookup existing both call the same functions in the actual system. In Elixir, it's kind of the same. I just have to redefine the agent, but you know that both of them just call trip lookup, trip insert, trip delete, whatever variant I have. But the nice part is that when I write my model, now I can write it like this. I have a new Shim module, but I can decide that some operations are going to be new insertion and existing insertion and unknown insertion and existing insertion. And they are all going to map to the same system calls or actual system calls I had before. But now my model, which is in the driver's seat, can make far more interesting predictions. I do have to change my generators a bit. This is a naive one where what I do is half the time I'm going to use keys that exist, half the time I'm going to use keys that don't exist. And it's the same in Elixir right now. It's exactly the same kind of implementation. Either a number or a value that was in the key, I get all my calls. And what I'm going to do is use the preconditions to put the constraints there. And let me start with the Elixir preconditions this time to make it fair to everyone. Insert new will only work if the value that I'm trying to insert does not exist in the map. Inserting an existing value only works if the value that I'm trying to look up in the map is already there. So I'm not getting error back from map fetch and so on. And so what I'm telling you is that the model, when it runs only some operations and some constraints. I am making sure the lookup existing is only called when the value actually exists in the tree. That's what I'm doing. And so same thing for that one. In Erlang. And again, this model is valid for a tree, but it is valid for key value store. It is valid for etcd or Paxos or any kind of algorithm you're running. If you have a key and a value in the lookup and you expect it to work the same as transactional memory called from a single process, the same model can be used for all of these. The same test can be used. The only thing you have to do is change the shim so that the model's calls map to the actual system properly. And so that's pretty neat. So I do that with the preconditions. I need to change the next state callback. Insert new, insert existing, and delete existing. What is interesting with this, you will notice that I no longer have to do the delete operation when I know the key does not exist. I'm explicitly saying that my model, when I'm deleting a value that does not exist, should have no change of state. It's a bit more declarative in its approach. It's far less imperative where I do detection based on the state and I always try the same thing. It becomes entirely declarative. If this is this call, no matter what my state, this is what I expect. And this declarativeness carries over even through the postconditions. And I have bolded the lookup postconditions, where before what I did was maps find the key in the state, in the value. And if the value is not there, I'll also expect it not to be there in the actual system and whatnot. With this new form, I don't even need to look at the state to know that looking up in the known value should never be found in the actual system. Even if the model were tracking it, I don't give a crap, right? The actual system should just not have it. And so I am really using the model to drive the testing now. I don't do any kind of lookups to make sure that, oh, is the actual system supposed to have this or not? No, when I'm looking up an unknown value, I should be getting that found no matter what my model state is. So these sequences of operations are much nicer and much more declarative at that point. And it really simplifies the tests in interesting ways. Right now, it's not a big deal because it's kind of trivial. But when you get into more complex systems, you find a point that you find yourself in situations where it's very hard to make sure that your test does not implement the same exact check as the actual system, right? And when we do it this way, the post condition on the actual system is guaranteed to not be the same operation as the one in the actual system, because the post condition is based on the model state and kind of disjointed there. And when I run these tests, then something interesting starts happening for these when I get my result. Let's use the deterministic variant. And when I run it this time in Elixir, I do get all kinds of new operations. And what I know is that now 70% of the time inserting is new values. I almost always look up and delete unknown values. In fact, I'm only inserting, looking up and deleting 5% of the values. And if you recall how we wrote the property, we don't do validation when we insert or delete. We only do validation when we look up a key. And so that means that only 5% of my operations are actually validating the state of my system. And that is drastically low. And it's the same thing if I do it in Erlang. I take the deterministic model and then, it's not called that. It's called this. And so when I run it the same way, I get exactly the same kind of value, right? In that case, I got a slightly higher percentage of values that were valid, but not significantly so. And because I worked a lot with Erlang as the first example, I'm going to do the adjustment of this system using specifically the Elixir version, so tree, model, deterministic tests. And in terms of quality control, this approach becomes very interesting because I can change how I generate commands here to use a different call. I'm going to use something called frequency instead of one of. And what frequency does is let me put the probability of each call happening. So here I'm starting with all of them on the same probability. Ooh, that's not the right keyboard shortcut. Here we go, here we go. Here we go, and here we go. And so right now, this is equivalent to one of because they all have the same probability. But what I'm going to do, for example, is say I want more of the rare calls to happen. So I might, maybe I still need to insert new keys to build a model. I'm going to increase the relative values of a bunch of them. And so I want to look up, insert existing, I actually don't want it to happen that one. I want to look up existing values far more often than I look unknown values. and delete existing values far more often than the rest, and smallest and largest, I don't really care. I trust these functions a bit more. And so I put this kind of relative probability into each one of the calls. And so when I run the test now, I should be getting different percentages. Oh yeah, that's shells are bleeding. And here I get the values. And now look up existing values, now 21% of the tests. Largest and smallest and overriding existing values over 4 smaller representation. And I can start playing with the quality of the commands I generate because I have far more control into what my model is doing. And so if I'm making a model, for example, for network partitions, something like that, knowing that an operation happens when the network is healthy or unhealthy, I'm able to really play with some kinds of values. Are all my writes happening on the same node, on different nodes, or something like that? The model is driving the implementation and the test quality. And the predictions I am able to make in my model directly impact the quality of the test and the checks that I do. I can do more stuff than just modeling, right? I could be adding invariants and postconditions if I wanted to. I could make a postcondition that what happens in there, I always check that the actual system is online, for example. There should never be a crash or something like that, even though the call succeeds. So all the other techniques that exist in property-based testing can be applied with this. It's just that in stateful tests, the model is king. It really, really leads everything that is going on. There's a lot more stuff that you can do with property-based testing, and they are mentioned in the book. There's targeted properties where you can write a very simple generator and ask the framework to generate larger, smaller values, to generate inputs that end up with the system under test being slower, or creating more disk churn if you want to. And it's kind of able to do that magically, and it's really, really interesting. You have state machine properties. And state machine properties are when the stateful model that you have from the user perspective has multiple states, even if it's only using a key value store underneath. If you have the state machine property where some calls are valid in some context and whatnot, they are useful for that. You've got stuff that covers shrinking, multiple types of properties. I've mentioned invariants, I've mentioned models. There are a few others. And another thing that you have in the book with the link right there is also the ability to, well, not the ability, but examples that show really how you grow properties, how you iterate to come up with good models, with good properties, how you apply them in a TDD system and all kinds of stuff like that. But we're about short on time, and this is what I had for today. I hope you enjoyed the presentation, and we're going to take questions, if we do have any.
Thank you so much for that, Fred. Sorry, there's a bit of time when it comes through. We do have some questions. Let me get them up for you. So if you look on the control panel there, you will see a few questions that have come through. Oh God, there's even more now. So let's go.
Well, currently I see no questions, so.
Yeah, so what I'll do is I'll make a note of these questions as well, and we can send over some written responses. So the first one here is, how would you suggest to tackle transition of a large code base involving multiple stateful components from standard testing to property-based tests?
So that's a very interesting question. The thing I would do is probably get a bit of practice on the smallest stateful component that you have and that you trust. Because one of the challenges that you have when you do property-based testing like that is that you never really know if the problem is in your model, in your property, or in your understanding of the system. And so if you start from a little component that you trust, you can at least get some practice building models more effectively and only having to debug the model. And then when you're better at debugging the model, understanding that the model does the right thing, you can start tackling the actual trickier implementations. The other thing is that usually you want to start with the more core critical components, and because that's where better testing is giving you more reward for the time you spend. But the big problem usually is coming up with a model, especially when you have systems that are very non-deterministic. Like if you're doing overflow control, you're dropping some requests on the ground or something, being able to figure out that, oh damn, you know, this is the request that should be failing, not this other one and whatnot, is really, really hard. And sometimes it's just unpredictable. And so you might want to do a thing where what you do is write a lot of simple, distinct models to test individual things. So if you're doing overflow control, you might have a simple property that no matter what kind of load I throw at it, I never go over this percentage of CPU or this given queue size. And so that's your property. And it doesn't check what gets dropped. It doesn't check priorities and stuff like that. But you can write another property later on that checks for priorities, for example, and stuff like that. And that approach of decomposing problems in more sizable chunks is worthwhile in programming in general, but still works well in properties. So multiple smaller properties can be a good idea at that point.
Okay, brilliant. The second question here is, does the shim need to be a gen server?
No, the shim doesn't need to be a gen server. I've had shims, for example, where what I'm testing is actually a web server. And so when I have the start link and the stop for the shim, I'm starting a Cobb or an Eli or a web server. It could be an Nginx web server for a component written in an entirely different language. And what the shim does then is it wraps my models calls into HTTP requests. If I'm doing REST, if I'm doing gRPC, it could be a gRPC client that wraps my models operations into the system. The shim doesn't have to be a gen server. In that case, it was the simplest because I'm testing Erlang and Erlang or Elixir and Elixir. It's really what we want the shim to be is that little thing that lets you map what your model is to what the actual system does. And it's also through the shim that you might test asynchronous operations more simply, because you might decide that my model is going to be synchronous, even if the system is asynchronous. And so what you do in the shim is you send the call and you lock and wait until you get the response. And so you can write a synchronous model for an asynchronous system by having the shim hide the asynchronous aspects of it, for example. So the shim is really the glue that lets you bridge your simpler model to the actual system. You do have to realize, though, that if you do an asynchronous operation like that with the shim, you risk missing out on all funny interleavings and parallel tests that could be tricky, which are covered in the book to some extent. But yeah, if the model is very, very simple to the point where it constrains what the actual system can do, you're going to get tests in scenarios where the model is respected. And so if the model doesn't map the real world, which is the flat earth theory compared to the real world theory, and all you did was restrict all the inputs, then you have not declared that the model doesn't work, but you have only declared that the model works under very strict constraints, essentially. So the shim is the glue to answer the original question.
Okay, so next question. Some errors might only manifest themselves in scenarios where multiple concurrent operations are requested on a system. So how can you use property-based testing to try pick up on these types of errors?
So there is a thing with the properties that we have in there, essentially only on stateful properties, where you can have the stateful property as we wrote, which is extremely sequential, but PropEr supports having a parallel version. And what it's going to do is going to create a kind of baseline of operations, take your list of commands and then create two subtrees of them and run them concurrently. You will not have guarantees that it will find race conditions with that. It's going to have a higher chance. If you really, really want to find race conditions for that, that's where a commercial license of QuickCheck might be interesting, because QuickCheck has polls, which is a custom scheduler for the virtual machine that will find all kinds of tricky interleavings with that, and play with the schedulers to make sure it triggers more of these errors. But otherwise, you can get some of them with PropEr. There is no guarantee you will get them. You might also want to look into more specialized tools like Conqueror, which has been written by Costas Agonas and his students, whose name I forgot right now, and are doing to do explicit testing of interleavings in some test scenarios. And so that one is interesting. Property-based testing does let you find about concurrency errors, but since, once again, it's always probabilistic, you have to maybe instrument your code a bit, which I show how to do in the book to cause errors to be more frequent. And usually it's about creating more scheduling points in your system so that you risk getting more tricky operations all fighting each other.
Okay, brilliant. Thanks, Fred. Next question. Is there a good example outside of the book on how you can integrate PropEr with the Mix Elixir project or use the Elixir syntax?
no, you don't want to do that directly. You want to use the PropCheck library. And the PropCheck library has decent documentation about how to integrate it. I don't know if there's anything outside of the book and the official documentation, but if you look at the official documentation of PropCheck, it does tell you how to add it to your dependencies, how to declare a property, how to use them, how to configure them. So the PropCheck package documentation is pretty good to show you how to adapt that stuff. Otherwise, I can show them kind of right now in there. Let me get the Elixir page and mix. Oh no, I was already in the Elixir version. And if you go into mix.exs, the thing I added there was adding the Elixir path for the test libraries to get them visible. But mostly the only thing you have to do is add PropCheck to your dependencies, use them in the test module, and then the macros are available. It's not really that much more complex than that.
Okay, next question. So how should I handle a case when the result given from a command has to be added to the state for a later lookup? And then he's given a little example.
Right, so I'm going to go look into the code directly. Can you tell me if the example was in Elixir or Erlang for that question?
We'll wait for his response and then move on to the next one. So,
okay. Yeah,
so the next question is, will you use property-based testing to practice TDD?
Yes, sometimes. The interesting aspect of doing property-based testing with a TDD approach is that usually when I do that, it's really exploratory. I start with a very, very simple model, no operations implemented. And I start with the simplest model that can work, which is an empty list with no operations. And I add operations one over each other and slowly build the model with the code to discover what I want to be happening. And what happens is that you might end up with a big model that is quite complex and you wouldn't have been able to write it the first time around, but you grew it at the same time as you grew the code. There are techniques to do it that make it a bit simpler or less complex. It is doable, but frankly, I think this is a kind of fresh field. I've been doing property-based testing for close to 6 or 7 years, and I've seen few projects that really use it in and out. And so I would tell you that it is possible, but almost nobody does it because few people know about property-based testing to the extent required to feel comfortable doing it to guide your design. One of my hopes when writing the book was to make that a bit easier and possible.
Okay, and then from the previous question from Eamon,
yes.
He said Erlang.
Erlang, okay, that's more comfortable for me as well. So I'm going to go, in the test file for deterministic model. And so what we might want to do, for example, if I had a question or a call that could be insert new, and I wanted it to return a transaction ID, for example, what I would need to do is in the next state value, there's a result here. This result variable is an opaque term. It's just a placeholder. It's not an actual variable that I can use as is. And so here I could decide that I'm supposed to get a transaction ID here, and I'm going to store both the transaction ID and the value in what I have. And so if I store the transaction ID, yeah, I wrote it funny, instead of my thing, I could store it that way. I cannot run operations such as check if it's okay or wrong or something like that, because when I'm generating the model, this is not a real value. PropEr underneath will return something like var, something like that, and it will know when the actual system runs that it needs to substitute them. So this opaque term, I can use it. And let's say I would instead use, last transaction is equal to transaction ID. I could use that in my system, and then when I generate a call, I could be adding a call like call in my model, blah, blah, blah. It's faster like that. Look up transaction, and the call would look into maps get last transaction from the state, and then this will get passed to the Shim module properly. So if I'm using a value that comes from the actual system, I need to use it as an opaque term. And this is another place where the Shim becomes really interesting, because when I have the deterministic Shim and I have, for example, a call that I expect to work or fail, then I can do something in here like if I expect the value to be, for example, case of OKX, then I just return X, and otherwise it's an error or something. And so the shim lets me remove all the terms I want to get rid of and get all the determinism I need in there. I do show how to make this work in the book. It's a bit kind of complex, and it's best to avoid it as long as you can. And that's where using the model to drive the tests keep things simpler. All right.
Thank you, Fred. What we'll do is we'll do one more question, and then I'm aware that there are 3 more questions here. So what I'll do is I'll make a note of them, and I'll send them over to you, and then we'll include them in the email with the recording that we'll send out after. So one last question, dear Fred, very polite. What would your approach to property-based testing to validate a program's memory management? For example, testing that a program always guarantees that no memory leaks exist.
So that one is interesting because I would think like an operator. If you are trying to find something as someone who is a DevOps person or a system administrator, what you would probably do is a soaking test. You start the system, you run the operations, and you look that the memory is always flat or doesn't seem to always be increasing no matter what is the load that is happening on there. And so if I wanted to run a property, you could do something quite simple like that, which would be, for example, 2 or 3 operations. Start the system, start the soak test, and what you look at, for example, could be logs or metrics, and those would be the actual values that you read and poll for, and your property would be that the metrics show you that the memory is not increasing indefinitely, right? You can draw the curve on the metrics and say that the curve should be flat or decreasing, or at least not always going up. It should be able to go down from time to time. And that could be the property. There's nothing that forces us to write a property that is essentially just unit tests. We can do it at the system level if you want to. And so that would be one way to do it. Another one would be if you're doing it specifically in your Erlang virtual machine, you have access to all the statistics about the memory allocators and stuff like that. So you could run the operations and just fetch the values directly, right? Have an operation such as do a call, and the shim waits until the call is done and all the memory is gone, and then you go call the allocator and you make sure that you see the behavior that you want, or that you see the number of reductions and garbage collections you wanted to see. And you're able to do that as a white box test as well. So that's probably how I would do it. I have never had to do that, but that would be my first approach. I don't know if it's great or not.
Yeah, that's pretty decent theory there. So we've still got a few questions. Let me see. I'll just make sure I've got them all noted down before anyone goes, and then we can make sure that we have them all. Okay. Yeah, that's all good. So what we'll do is we'll send this over to you, and let you're free to go, Fred, after this. Thank you so much for this webinar. It's been fantastic, and we've had great feedback as well. So thank you for people who have appreciated Fred's time today. So that's all for today, and I hope you've enjoyed. We'll be back soon with another webinar. Keep that under wraps for now, and we look forward to hosting that. Otherwise, thank you, Fred, and we'll speak soon.
All right. Thanks, everyone, for attending.
Bye then.